Next topic, linear transformation. Linear transformation. Now, as you know, transformation means what? Like in multiple integrals, change of variables. Cartesian coordinates to polar coordinates, or spherical coordinates, or cylindrical coordinates. Nothing but it's a transformation from Cartesian coordinates to other coordinate system. Same in matrices also, there is a transformation. One is linear transformation, another one is orthogonal transformation. First, let us see what is meant by linear transformation. Consider a set of n linear equations. What we are considering, only linear equations. Linear equations means in those equations all the variables must occur at degree 1. Okay, and what is a set of n linear equations? Here y1 equal to a11 x1 plus a12 x2 and so on a1n xn, first expression, and y2 equal to a21 x1. The right hand side expression is well known for you. That is a system of matrix system of equations, a2n xn and so on. How many equations I told? N equations. Therefore, this is yn equal to, this is dash yn equal to a nth equation, an1 x1, a n2 x2 and so on, a nn xn, Take this as equation 1. And here, to represent the system in matrix form, let capital Y equal to, I'm taking capital Y as y1 y2 yn, y1 y2 yn. Then it's a column matrix, y1 y2 and so on yn. Similarly, the matrix X, the same logic, solution vector, that is x1 x2 xn. And what is the coefficient matrix? And a equal to what? The coefficients of x1 x2 xn. That is clearly a11 a12 and a1n, a21 a22 and so on a2n, and lastly nth row an1 n2 ann. This is the matrix of order n by n, and this is n by 1 column matrix. This is also n by 1 column matrix. Now, then the set of equations, then the set of equations 1 can be written in matrix form, can be represented in matrix form, as y equal to ax. Right side matrix, what is the right side? Y terms are there, therefore y equal to, left side is left side is y and right side is what? Matrix A is there and x is there. This is equation 2. Y equal to ax, which transforms, what is this represents? Nothing but which transforms the set of n variables. The set of n variables. What are the variables? x1, x2 and so on xn to the set of n variables. What is that variable? What are those variables? y1 y2 yn, y1 y2 and so on yn. Okay, so this is transformation, transforms these variables to these variables. So x is transformed to what? X variable is transformed to x. This one is called, so thus equation 2 represents, equation 2 is a transformation. First thing, equation 2 is what? Transformation. Equation 2 is transformation. Then what about linear transformation? Let us see. Equation 2 is a transformation which transforms x into y. The variables x are transformed to variable y. That means what? If I give these x variables, all these variables are transformed to y variables. This is called transformation. First thing, simple definition. So write the system of equations where the left side vector is y, right side matrix is a and x. So x is shifted to y by using what? This matrix. When x is multiplied by a, then it reduces to y. Then here, therefore, here the matrix A is called, here the matrix A is called matrix of the transformation. A is called matrix of the transformation. Matrix of the transformation. Now the definition, linear transformation. Linear transformation. What is linear transformation? This equation to consider the transformation. Consider the transformation. What is that? Y equal to ax. Consider the transformation y equal to ax. Y equal to ax. This transformation is called linear. This transformation is called linear transformation. Linear transformation. Linear transformation. If it is additive, or you write like this, if it satisfies the following conditions. If it satisfies the following conditions. What are the conditions? The first one is the following conditions. The first one is A into, you write like this, A into, there are two vectors, x1 plus x2. Then this must be equal to ax1 plus ax2. Additive property. This is called additive property. This is additive property. Next one. Second one is constant multiple of with any vector. That means a into some, I will take cx. That is equal to c into ax. C is any scalar. These two conditions. One is, this is the linear property, additive linear property, and the next one, multiplication of a transformation by a constant c, or these two, 1 and 2 can be 1 and 2 conditions. 1 and 2 can be together, can be written combinedly as how to write this is single expression, a into c1 into x1 plus c2 into x2. Here constant multiplication by a constant is there and addition of two vectors is there. So this equal to c1 into ax1 plus c2 into ax2. This condition is enough. Then the transformation y equal to ax, this transformation is there now, y equal to ax is called linear transformation. Just definition is important, okay, in linear transformation. Another one is what? Orthogonal transformation. orthogonal transformation. Here, what is the definition of orthogonal transformation? The linear transformation, y equal to ax is said to be orthogonal, is said to be orthogonal transformation, is said to be orthogonal, is said to be orthogonal transformation if it transforms, if it transforms, listen carefully, if it transforms x1 square plus x2 square and so on plus xn square into y1 square plus y2 square and so on plus yn square. What is this? The transformation y equal to x is said to be orthogonal if it transforms what? This x1 square plus x2 square plus xn square into y1 square plus y2 square plus yn square. And the matrix of transformation, the matrix of orthogonal transformation, the matrix of orthogonal transformation is called, the matrix of orthogonal transformation is called orthogonal matrix, is called orthogonal matrix. You know what is meant by orthogonal matrix? What is that orthogonal matrix? Anyone? A into A transpose equal to I. That is orthogonal matrix, right? Now, let us see. 1 point, this much is enough. But when two matrices are said to be orthogonal, do you know? Okay. What is a orthogonal transformation? What orthogonal matrix means what? A into A transpose equal to I, or A transpose into A equal to I. Okay. Now, let us see. We have x transpose into x or x into x transpose, whatever it is. What is x actually? X means x1, x2, xn. Column vector, transpose means row. And what is this? X means x1, x2, xn. Right? Transpose into this. If I multiply this, what I'm getting? X1 square. If I multiply these two matrices, we are getting x1 square plus x2 square plus xn square. Similarly, y transpose into y also is what? y1 square plus y2 square up to yn square. Yn square. This is called inner product. This is called, this matrix into this matrix is known as inner product of the matrices x and x transpose. Therefore, if y equal to ax is orthogonal transformation, y equal to ax is orthogonal transformation, then what happens? See, then x transpose into x, what I told, this x transpose into x is transformed to what? Y transpose into y. What is the definition of orthogonal transformation? Orthogonal transformation means what? This one, x1 square plus x2 square is transformed into what? y1 square plus y2 square, yn square. Therefore, by using orthogonal transformation, this, what is x transpose into x means what? X transpose into x means what? x1 square plus x2 square plus xn square is transformed to y transpose means y1 square plus y2 square and yn square. Then what I have, what is y equal to actually ax? Done. So y transpose means what? Ax transpose, and y is ax. Y is ax. Let us see what happened here. You know, AB whole transpose is what? Property B transpose A transpose. Okay. Using this, this becomes x transpose A transpose into A into x. Isn't it? Right? So that is equal to x transpose A transpose into A together, these two matrices, into x. Into x. And see, this implies is what? X transpose X equal to this, X transpose X equal to this. When these two are equal, these two are equal only when this is possible, only when this product must be I, only when this product must be I. When this is I, X transpose I into X is nothing but what? X transpose X. X transpose X. Done? Okay. Therefore, what I am having, this A into A transpose equal to I means what is this transformation is nothing but orthogonal transformation. Okay. Done? This is the important point. I'm getting finally this conclusion. This is about orthogonal transformation. Remember always, orthogonal transformation must be, it transforms sum of squares into another sum of squares. Sum of squares of X into sum of squares of Y's. This is called orthogonal transformation. Just this is notation purpose. And coming to, if I want to prove any matrix as orthogonal matrix, just you consider A into A transpose and make it as, show it as I, then matrix is said to be orthogonal matrix. Okay, this is a small topic, linear transformations and orthogonal transformations. Anyway, we are having these two again in diagonalization of a matrix, which I'm going to discuss now. What is the next topic? Reduction to diagonal form. This is very important. Reduction to diagonal form. Reduction to diagonal form. Okay. What is the theory here? Just understand the theory. See, the statement is what? Statement is, if a square matrix, only square matrix, if a square matrix A of order n, has n linearly independent eigenvectors, n linearly independent eigenvectors, then a matrix P, then a matrix capital P can be found such that P inverse AP is a diagonal matrix. P inverse AP is a diagonal matrix. Okay, this is the statement and nothing but a theorem. Just I will make a rough proof by considering one 3x3 matrix. To prove this statement, to prove this statement, let us consider a 3x3 matrix, a matrix A of order 3, a square matrix of order 3, right? Okay, see the statement, all of you. Once again, I'm explaining. Matrix A is there, and if it is order n, then it must possess n linearly independent eigenvectors. I told you what is linearly independent eigenvectors. In eigenvalues and eigenvectors, always remember matrix A is given. And you write characteristic equation that is equal to 0. Find the eigenvalues. Lambda 1, lambda 2. If it is n by n matrix, n eigenvalues are there. If all these eigenvalues are distinct, real and distinct, if all these eigenvalues are distinct, maybe real or complex, eigenvalues may be complex also. Real or complex, distinct eigenvalues, definitely, then each eigenvector is linearly independent. Already we have seen that. Now, when any eigenvalue is repeated, like our previous examples, 2 to 8, 2 is repeated 2 times. If any eigenvalue is repeated, and for the repeated eigenvalue in the echelon form, if it is repeated 2 times, I have to get 2 0 rows. Then only I will get 2 linearly independent eigenvectors. two linearly independent eigenvectors. Our first problem in eigenvectors, one eigenvalue is repeated, but we are getting only 1 0 row. Therefore, there we are getting only one independent eigenvector. The other is dependent on it. Such type of matrix cannot be diagonalizable. Such type of, that means when eigenvectors are dependent on each other, then we cannot diagonalize them. This is very important point. And when eigenvectors are linearly independent, yes, it is diagonalizable. By using what? P inverse AP. I can find a matrix P, and the transformation P inverse AP is nothing but a diagonal matrix. Now, let us see the proof by considering 3 by 3 matrix. Now, since A is 3 by 3 matrix, A is 3 by 3 matrix, let how many eigenvalues will be there? 3 eigenvalues. Let lambda 1, lambda 2, lambda 3 be the eigenvalues. And what are the eigenvectors? x1, x2, x3. I'm taking x1, x2, x3 be the corresponding eigenvectors. Be the corresponding eigenvectors. Okay. 3 by 3 matrix. Therefore, I'm taking eigenvectors as first one capital X1, x1, y1, z1, and x2 eigenvector as x2, y2, z2, and x3 eigenvector is x3, y3, z3, x3, y3, z3. These are the eigenvectors. Now, grouping these 3 eigenvectors, grouping these 3 eigenvectors, we have grouping these 3 eigenvectors. We have grouping these 3 eigenvectors means write the eigenvectors together in a matrix. Together in a matrix. What is this? x1, y1, z1, x2, y2, z2, x3, y3, z3. This matrix is called P. This matrix denote. That means this matrix P, whatever I given in the statement, this matrix P is what? It is formulated by grouping the eigenvectors. In brackets, you can write that is P is formulated by grouping the eigenvectors. By grouping the eigenvectors. By grouping the eigenvectors. Then what happens? See, therefore, what is P? Therefore, what is my matrix P? Once again, I am writing this. Matrix P is, this is x1, y1, z1, x2, y2, z2, x3, y3, z3, x3, y3, z3. See, and what is the transformation is it is given? Now I got matrix P is here. It is multiplied by what? A. Now let me multiply this by AP. A. Now A into P. A into P equal to A into what is matrix P? This is nothing but what? x1, x2, x3. Done. So I'm writing that x1, x2, x3. Now clearly this is nothing but ax1, ax2, ax3, linear property, ax3. But what is ax1? Since what is ax1? Anyone? What is ax1? It is nothing but lambda 1 x1. This is nothing but lambda 2 x2. This is nothing but lambda 3 x3. Now for this I'm giving the justification. Let a lambda 1, lambda 2 are the eigenvalues and x1, x2 are the eigenvectors. So let me write here. Therefore, a1 x1 equal to lambda 1 x1, correct? Lambda 1 is eigenvalue of a1. Sorry, a, not a1, a. This is a. Ax1 equal to lambda 1 x1, ax2 equal to lambda 2 x2, ax3 equal to lambda 3 x3. This is true because lambda 1, lambda 2, lambda 3 and x1, x2, x3 are eigenvalues and eigenvectors of matrix A. Okay. So using that, ax1 can be replaced by lambda 1 x1, ax2 is lambda 2 x2 and ax3 is replaced by lambda 3 x3. Right. Then what happened next time? Let us write x1, x2, x3 vectors in this one. That is equal to, let me write what is x, substitute x1 this is equal to, substitute x1, this is equal to lambda 1, what is x1? X1, lambda 1 y1, lambda 1 z1, lambda 2 x2, lambda 2 y2, lambda 3 y3, lambda, sorry, 2 z2, this is what? z2, lambda 2 z2, lambda 3 x3, lambda 3 y3, lambda 3 z3. Just I'm substituting x1, x2, x3 values. Now this matrix can be written as, whatever this total matrix can be taken as product of two matrices. What is that? x1, x2, x1, y1, z1, x2, y2, z2, x3, y3, z3. This is multiplied by lambda 1, 0, 0, 0, lambda 2, 0, 0, 0, lambda 3. If you take the product of these two, you will get this entire matrix. You will get this entire matrix. So what is this matrix? First matrix is nothing but P. And this second matrix is there now. You denote that D. Yeah. D stands for diagonal matrix. In this diagonal matrix, what are the diagonal elements? Lambda 1, lambda 2, lambda 3, lambda 1, lambda 2, lambda 3. These are the diagonal elements which are eigenvalues. Lambda 1, lambda 2, lambda 3 are eigenvalues. And what is this matrix? This is left side, AP is there. AP equal to. Done. So what is matrix A can be written as from this? Let us pre-multiplying on both sides by P inverse. P inverse AP equal to P inverse PD. P inverse PD. Okay. Multiplying on both sides by P inverse. Okay. Then this is P inverse AP is equal to what? P inverse into P into D, associative property. That implies P inverse AP equal to what you will get? D. P inverse AP equal to D. Therefore, where D is the diagonal matrix. This is the proof. What I need. Finally, what? P inverse AP is what? A diagonal matrix. That's what we are getting here. P inverse AP equal to D, which is a diagonal matrix. Which is a diagonal matrix. Which is a diagonal matrix. Now, points. Note 1. What is the first note? Note 1. First note 1. P inverse AP is called this. What is this? Is nothing but this matrix is transformed to D. P inverse AP is called similarity transformation. Similarity transformation. Similarity transformation. Second note. The matrix P is called the matrix P. What is this P? Grouping the eigenvectors. If n vectors are there, n. So I will not write this. I will not write this. The matrix P. What is this matrix P? Is called matrix transformation. Is called matrix transformation. Matrix transformation. And P is over. Or this is a matrix transformation. Sometimes it is also named as model matrix. Also named as model matrix. The first point and second point. And therefore, what is this P inverse AP? Now onwards, it is called similarity transformation. And third note, see, this is important. Third one, what is that? You write like this. On the matrix A, if we apply similarity transformation, what is the meaning of here similarity transformation? That is, matrix A is post multiplied by P and pre multiplied by P inverse. Similarity transformation, then it reduces to what? It reduces to diagonal form. It reduces to diagonal matrix. D in which the diagonal elements are eigenvalues of A. Eigenvalues of A. Okay, this is very important point. Last point. P inverse AP is nothing but D. That means what? On matrix A, if I apply transformation, similarity transformation, P inverse AP, then it goes to diagonal matrix, and in which diagonal positions are nothing but eigenvalues of the matrix A. And what is the see, one more point I will tell you. If P is x1, x2, x3, this order, if I group the eigenvectors in this manner, first eigenvector, second eigenvector, third eigenvector, then D will be what? Lambda 1, 0, first one lambda 1, second 2, 2 position lambda 2, 3, 3 position lambda 3, or this is the first point in fourth one. If I consider P as something x2, x3, x1, I can group like this also anyway. Right? I will write second eigenvector first, third eigenvector, lastly first eigenvector. Then what is the diagonal form becomes what? You will get first lambda 2, then lambda 3, then lambda 1, like so. Like so. Okay, that means other cases for P. This is similarity transformation. And one more point. What is the use of this similarity? Another use of similarity transformation. I can find powers of a matrix. I can find powers of a matrix. Powers of a matrix means what? If matrix A is given A square, A cube, A power 10, like that. Powers of a matrix. Okay. Using similarity transformation. Using similarity transformation, we can find the powers of a matrix A. Powers of a matrix A. See how it is possible. First one, what is this? This matrix P inverse AP equal to what? D. Isn't it? What is D stands for? I'm considering this order. Right? Okay. I will write P inverse AP equal to D, because I need what? I need what? A I need. So let me pre-multiplying by P inverse P. That is PD. That means what? Multiplying on both sides by matrix P, pre-multiplication. Then what this gives? One can write P inverse into P AP equal to PD. Done. P inverse into P is nothing but A. I into A is nothing but A. This is over. Next one, I need only A. So post multiplying by now A P P inverse. So P D P inverse. Multiplying on post multiplying. This is called post multiplying by P inverse. Then A into associative property holds in matrix product PD P inverse. Therefore, what is this? AI equal to PD P inverse. Done? Okay. That is equal to A equal to what? Now I'm getting PD P inverse. This is important. This is A power 1. Now, all of you. I want A square. A square is nothing but A into A. So I can write PD P inverse, PD P inverse. Done? Now, since it is associative, I can write PD P inverse into P, D P inverse. So PD, this is I, D P inverse, right? So this is P D into D P inverse. That is equal to P D square P inverse. P D square P inverse. Therefore, A square is what? P D square P inverse. This one. A value and A square value. That means whenever square, here if it is square, then D square. Similarly, what I'm getting, I can write. Similarly, I can write A cube equal to P D cube P inverse. P cube D inverse. In general, if I want to find A power n, then what this becomes? P D power n P inverse. That's it. This is one use of to calculate powers of n. This is about diagonalization by using similarity transformation, the first topic. Next one is orthogonal transformation is there. Diagonalization by using orthogonal transformation. Any doubts in this one topic? Any doubts? If no doubts, I will proceed for the problem. First problem, reduce the matrix A equal to -1 2 -2 1 2 1 1 -1 -1 0 to the diagonal form, and the students, here election campaigning is going on, so some sounds are coming from outside, so don't bother. Solution: reduce the matrix A to diagonal form. Here, see, there are two important points. If the question is reduce the matrix to diagonal form, it's enough to find up to eigenvalues. And in the question also specify the matrix transformation, then you have to find the matrix P also. So one I'm giving also specify the matrix transformation. Okay, then first thing, what is a matrix A? To reduce the diagonal form, what I need? Diagonal form means what? In D, what are the elements? Eigenvalues. So first I have to find eigenvalues of the given matrix. Okay, first we have to find eigenvalues of A. For that, what is the procedure? Eigenvalues of A procedure, the characteristic equation of A is what? Determinant of A minus lambda I equal to 0. So what is this? -1 minus lambda 2 -2 1 2 minus lambda 1 -1 -1 negative lambda equal to 0. From the diagonal positions, you subtract lambda. This gives what? Lambda cube. After simplification, lambda square minus 5 lambda plus 5 equal to 0. Is a cubic equation. How to find roots of this equation? First one, by trial. Trial means substitute some value. By trial, if I put lambda equal to 1 here, lambda equal to 1, what is this? 1 minus 1 minus 5 plus 5, yeah, 0. So by trial, lambda equal to 1 satisfies this equation. Therefore, lambda equal to 1 is one root. Next, let us go for synthetic division. You know synthetic division, 1 cube quotient, next one square quotient, lambda quotient, and a constant. Then what is the root? My root 1, 0. 1 plus 0, 1. 1 into 1, 1. Add these two, 0. 1 into 0, 0. Minus 5. 1 into minus 5, minus 5. This is 0. Lastly, you have to get 0. And these are the quotients of what? These are the coefficients of quadratic expression. What is that quadratic? Lambda square plus 0 into lambda plus minus 5 equal to 0. So what is this? Lambda square minus 5 equal to 0. So lambda equal to plus or minus root 5. Two roots are here. Therefore, eigenvalues are lambda equal to 1, root 5 minus root 5. Since eigenvalues are distinct, the corresponding eigenvectors are definitely what? Corresponding corresponding eigenvectors are linearly independent. Linearly independent. Definitely, it's a theorem. Linearly independent. So no need to check the independency of eigenvectors because of eigenvalues are independent, distinct. Now case 1. What is this first one? I have to find matrix transformation is required. Therefore, I have to calculate eigenvectors for lambda equal to 1. For lambda equal to 1, consider the system. What is that system? A minus lambda I into x equal to 0. So this is a minus I into x equal to 0. So what is this becomes? A minus I 1. Lambda is 1. So this becomes minus 2, 2, minus 2, 1. This becomes 1, 1, negative 1, negative 1, and a negative 1 into x equal to 0. So what is this one? R3 plus R2. That's enough. I think I have to convert these two to 0 now. Let me write. What is the operation? First one is R3 minus 2R1. Next one R2 plus R2, 2R2, sorry. 2R2. This is also a mistake. This is what? 2R3. 2R3 minus 2R2 R1. So what is this is minus 2, 2 minus 2, and this becomes 0. 2 minus 2, 0. This is 2. 2 minus of minus 2, this is 4. If any corrections, correct me. This is 2 multiplied by 0, and this is minus 2 plus 2, 0, and this is what? Minus 2, minus 2, minus 2, minus 4 will be there. Minus 4 will be there, isn't it, right? So another operation is what? R3 plus R2. Simple. This is minus
Sir,
2.
second row, second column, 4.
This one?
Yes.
This is what? 2. 2 plus 2. Yeah, 4. Correct. That. Then it is echelon form. Huh? No. Some mistake is there. What is lambda equal to 1 now? This is minus 2. 2 minus 2. Wait.
Second row element 0, 4, 0, sir.
0, 4. This is 2. Yeah. This is 0. Correct. Now, already this is 0. I have to get this one 0, no? Compulsory.
Third row also 0, minus 4, 0, sir.
Wait. This is 2 or 3. 2 minus 2. Minus 2, minus 2. Yeah, minus 4. Correct. And this is minus 2. Minus 2 plus 2. This is 0. Correct. Now it is right? R3 plus R2. Now it gives definitely 0, 0, 0. Any corrections? So 1, 0 is there. Rank is 2 less than 3. The number of unknowns. Therefore, system has non-zero solution. I will not write all these things, one independent variable like that. So what I am getting, minus 2x plus 2y minus 2z equal to 0 and 4y equal to 0. From this, what is y value? 0. When y value 0, what is this becomes? Y 0, 2x equal to minus 2z. So x equal to minus z. Combining these two, x equal to minus z and y equal to 0, we have x by 1 equal to y by 0 equal to z by minus 1, or you can take x by minus 1 like that. Therefore, eigenvector is, first eigenvector is what? 1, 0, negative 1. First one is over. Coming to second one, case 2. Lambda equal to root 5. Lambda equal to root 5. Then the system is a minus lambda into x equal to 0. That is a minus root 5 I into x equal to 0. This gives what? What is the matrix? Minus 1, minus root 5, 2, minus 2, 1, 2 minus root 5, 1, negative 1, and negative root 5 into x equal to 0. Done. So what are the operations? First one, see, I have to convert this to 0, this to 0. So I will write 1 plus root 5 into R2 plus R1. Is it correct? This is minus common. So minus of 1 plus root 5. Yeah, first one is right. Next one, 1 plus root 5 into R3. This is minus. So I have to subtract from this. So minus of 1 plus root 5 to minus 2. This is 0, this is 0 without any doubt. Next one, coming to this position, this one, this is multiplied by 2 minus root 5. 2 minus root 5 into 1 plus root 5. This is 2. 2 root 5 minus root 5 plus root 5 plus root 5 plus root 5, and another one is minus 5. So this becomes what? Minus 3 plus root 5. If it is mistakes, correct me. Okay. And this position, 1 plus root 5 minus 2. So this becomes minus 1 plus root 5 coming to this position. Minus 1 minus root 5 minus 2. So minus 3 minus root 5 I am getting okay. And next position, let me check this position once again. 1 plus root 5 into 2 minus root 5 now.
Sir, plus R1 also is there, no, sir? 1 plus root 5 into R2 plus R1.
Right. This is, I did only first one, right? Minus R1 means what? Here, my plus R1. Correct? Now, just wait. Once again, I will do. If anyone did, please tell me directly. This is 1 plus R5, 2 minus root 5 into 1 plus root 5 plus R1. I did. Plus R1 means plus 2. Okay. Now this is 2. 2 root 5 minus root 5 plus root 5, and this is minus 5 plus 2. So this is root 5 minus 1. This is minus 1. Next one. I think this is correct. Yeah, this is I did. Right. Coming to third one, minus 1 minus root 5 minus 2. Minus 3 minus root 5. Next one, coming to this position, 1 plus root 5 into minus root 5. Minus root 5. Minus R1 means plus 2. This is what? Minus root 5. This is minus 5 plus 2. So this is minus 3 minus root 5 I'm getting. That. Next step is directly R2 divided by minus 1 plus root 5. R3 divided by minus 3 minus root 5. It then matrix reduces to minus 1 minus root 5, 2 minus 2, 0, 1, 1, 0, 1, 1 into x equal to 0. Done. So next operation is R3 minus R2. Minus 1 minus root 5, 2 minus 2, 0, 0, 1, 1, 0, 0, 0 into x equal to 0. So directly, what is minus 1 minus root 5 into x plus 2y minus 2z equal to 0. And next one is what? Y plus z equals to 0. From this, I will get y equal to minus z first one. Okay. And next coming to this, minus 1 minus root 5 into x equal to, if I put y equal to minus z, minus 2z, minus 2z, 4z will be there. So what I'm getting this is, you write, let us write for this one, z, minus 1 minus root 5 by 4 into x equal to z, and 1 plus root 5 by 4 into x equal to minus z. Minus z. Now let us combine these two. For minus z, combining we have 1 plus root 5 by 4 into x equal to y equal to minus z. Done. Okay. Therefore, what I can write from this? Anyone? I can write this is 4 by y, this is x by 4, y by 1 plus root 5, z by minus 1 minus root 5. I can write. Any corrections? Therefore, x2, second eigenvector is what? 4, 1 plus root 5, minus 1 minus root 5. Any corrections? Please check. This is, I am substituting minus z here. So this becomes 4z. Done. 1 plus root 5, exactly right. This is z minus z. I am equating to minus z on both sides. Correct. Okay. You can rationalize this by 1 minus root 5 also. Okay, is the second eigenvector. Now case 3, fastly, because only 5 minutes are there. What is lambda equal to what? Negative root 5. Then a minus lambda into x equal to 0. So a plus root 5 into x equal to 0. Then what is this? A plus root 5 minus 1 plus root 5 will be there. 2 minus 2, 1, 2 plus root 5, and this is 1 minus 1 minus 1, and this is root 5 into x equal to 0. X equal to 0. Okay. Now, operations are what? Minus 1 plus root 5 into R2 minus R1, minus 1 plus root 5 into R3. This is negative is there, therefore plus R1. So what is this? Minus 1 plus root 5, 2 minus 2, this is 0, this is 0. Coming to this part, minus 1 plus root 5, 2 plus root 5, minus R1, minus 2. So this is minus 2, minus root 5 plus 2 root 5, plus root 5, plus 5 minus 2, 5 minus 4, 1, 1 plus root 5. Coming to this part, minus third, 1 plus root 5, minus of minus 2 plus 2. So this is also 1 plus root 5. Coming to this, multiplied by minus. So 1 minus root 5 plus 2, 3 minus root 5. Coming to this, 3 position, minus root 5. I can write plus 5 minus 2. 3 minus root 5. 3 minus root 5 into x equal to 0. So obviously, what I'm getting finally, you write the operations 2 minus 2, this is 0, 1, 1, this is 0, 0, 0 into x equal to 0. Divided by 1 plus root 5, second row, 3 minus root 5 by third row, then subtract. Then what I'm getting, minus 1 plus root 5 into x plus 2y minus 2z equal to 0 and y plus z equal to 0. From this, y equal to minus z. And what this becomes, minus 1 plus root 5 into x equal to, this is minus z, this is minus z, minus 2z, 4z. So what I'm getting, minus 1 plus root 5 into x by 4 equal to z. I need minus z. So let us take minus common here. 1 minus root 5 by 4 into x equal to minus z. So equate these two for minus z. So what I'm getting, therefore 1 minus root 5 by 4 into x equal to y equal to z by minus 1 or minus z. You can write minus z. Therefore, what is this one? This is equal to, this implies I will write x by 4, y by 1 minus root 5, z by, what is this? minus of 1 minus root 5. So third eigenvector is, therefore third eigenvector is what? 4, 1 minus root 5 minus of 1 minus root 5. Right? Therefore modal matrix P. Therefore modal matrix or matrix transformation P equal to, what is this? I have to group these three eigenvectors. So what is this? Third eigenvector is, I'm having 4, 1 minus root 5. This is root 5 minus 1. Okay. And what is the second eigenvector? 4, 1 plus root 5, 1 minus root 5. 4, 1 plus root 5, 1 minus root 5. What is the first eigenvector? Anyone? 1. I think y I got 0. Check it. Correct?
Yes, sir.
Right. That's it. Next step is what? Therefore, using similarity transformation, you have to write just this statement using, all of you, this is important. Last statement, how diagonalization is possible. Using similarity transformation, we have, what is that? P inverse AP equal to D. That is what? D stands for what? Lambda 1 0, 0 lambda 2 0, 0 0 lambda 3. I'm writing here, first one is lambda 1, lambda 2, next lambda 3. According to the order, this is x1, this is x2, this is x3. According to that, write the eigenvalue in these diagonal positions. That's it. So what is the diagonal form? Lambda 1 is what? 1 0 0. What is the next eigenvalue? I have considered positive root 5. Third eigenvalue negative root 5 is the required diagonal form. No need to prove. Already we proved the theorem. So this statement is very important. Similarity transformation, P inverse AP always reduces to diagonal form. Okay, and the matrix transformation is this one. Okay, this is one problem. In the next class, I will deal with another problem. Please practice these problems, all of you.